So what we're going to look at now, motion in a circle. Okay. So there's something, there we go. Motion in a circle. So there's some small things I need to cover that we haven't done in maths class yet. They're not too difficult, but we will do them in maths class.
We will?
We will. When we get to trigonometry. Motion in a circle. So if you think about it, we've only really have done two types of motion so far. We've done motion in a straight line in one dimension, and then we've done this type of motion in two dimension. But this here is really just a mixture of this one plus this one, isn't it? It's nothing really special. So they're the only two we've done so far. So we're going to look at a special case of motion in a circle. Okay. So before we start, just let's talk a little bit about language here. Okay. Well. Okay, this here, theta is the angle. Now, this piece here in red, which I call S, S we call is the arc. And then finally, I'll do it in blue here. Very good. The or there is called the radius. Okay? Yeah. Now, what's important, we do not use degrees. Yes. Degrees. We use radians. 1 radiant is approximately 58 degrees. So this is a different unit. Okay, we don't use the unit degree. We use the unit radians. If you want the exact amount,
Will you give it formula?
yes, I'll give it to you. I don't know if it's in the book, but 1 radiant is pi over, sorry, 2 pi, no. This is one of these situations where the teacher just needs a few seconds to gather his thoughts and get it. 2 pi is 360, so pi, 180 over pi, yeah, okay. So if you want the exact number, just type this in on your calculator. So can you type that in and tell me what you get? Is it about 58?
It's 57.295.
Oh, it's 57. Okay, 57. So we do not use degrees. If the question used degrees, you should change it to radians. Just like in chemistry, you shouldn't really use Celsius. What should you use? You should really use Kelvin. Okay? No, you don't need to, but you should. I can't think of a situation where you must use Celsius and not Kelvin.
So why must we use radians and degrees?
Dude, I'm teaching you it right now. If you wait a moment, you'll see the reason why. Sorry, it's the only thing I could think of as a reply. So just give me a moment, I'm getting to it. So, you must use radians instead of degrees. Just like we must use meters, seconds, kilograms, and so on. And the reason for that is because the formulas that we use only work if we use radians. Okay? So just like in chemistry, you know, I don't know if you've done it yet, the ideal gas law, PV equals nRT. Yeah? You will do it, and you do it in physics as well. PV equals nRT. Not yet. That formula only works if the temperature is in Kelvin. So for some formulas in physics and chemistry, they only work if you use the right units. So these formulas we're going to do today, they only really work if you use radians. Radians. Okay? And the first formula to demonstrate that is that the angle equals the distance divided by the radius. That's your first formula for motion in a circle.
Sorry.
Yeah?
PV and RT works with Celsius. If we use the right units for our...
Yeah.
For the wells,
But you're going to a lot of trouble then. You have to change the unit, yeah.
is that a unit for angle?
Which,
I mean the circle and
oh no, that's a Greek letter, theta. Is-
what does that stand for?
Just stands for angle, yeah. It's not a unit, but it's the letter for angle. Okay? Right, well that's just the first formula. A lot of times people write it like this, really, because often what happens is you know the radius and you know the angle and you want the arc.
Is it arc length or just arc?
Arc length, yeah. Now, it's very important. The unit for radius, or I should say the dimension for radius, what's that? That's length, isn't it?
Yeah.
And what unit do we use?
Meters.
Meters, okay. Now, the unit for S, what do you think that is? Length. And what unit? Meters. So if I put that into this formula, what's the unit for angle here?
Meters squared.
No,
Nothing. One.
it's length over length, which is 1, which is no unit. What does that mean? That means that the angle never changes, even if you change from using meters to feet to kilometers and so on. In other words, radians is actually universal. It does not depend on the units. If you use SI, or if you don't use SI, if you're in America, you do not need to change anything about the radians. It is free of dimension, dimensionless. Okay? So that's just a good thing to know. It's useful to know that. It's helpful. Okay, now, next. Do you have that? Yes? What's wrong, Dana?
That theta is radian.
Yeah, we call it radian. So, like, for example, here. If I say theta equals 1 radian, that's about that much. And then this would be about 2 radians, roughly. So I sometimes say radians is a unit. And yeah, it is a unit, I suppose, but at the same time, it's not really a unit. But I think it's easy for students if we always say radians. So if I say theta equals 1, I really mean theta equals 1 radian. Okay? But it's not really necessary to say radian. It's just helpful.
Is there a T in there?
A T?
In the word radian.
Oh, sorry, did I not write it down? Radians.
No,
Yeah.
it's plural. Yeah, but both one.
Radian. Radians.
One radian.
Yeah, I'm sorry if it sounds like I'm putting a T in there. I don't think there should be a T. Yeah. Radian. Radians. No T. Okay. Now, next. So, we're talking about motion in a circle. So, if this starts here, and then let's say 1 second later it moves out to here, and then let's say this angle is 1 radian. What we're saying is in 1 second we moved 1 radian. So this gives us an idea of speed, doesn't it? Like, for example, if it did 1 radian in 2 seconds, is it going faster or slower? Slower. So we have this idea of what's called angular speed or angular velocity. I will prefer to say speed, but here it's velocity. Angular velocity, yes, and it's omega. And it's the change in the angle divided by the change in time. Or it's the rate of change of the angle. Or again, it's the change in angle per time. Whatever way you want to say it. Reject. Okay. That's okay? So that's angular velocity. Okay. I think in the book they write it like this. And that's okay, but I don't like that so much because I really want to emphasize that it's the change in the angle divided by the time it takes. So it's better to write it like this. Okay. So how many formulas do we have so far? We have 2. We have distance equals r theta, and angular velocity equals theta over time, like that. Now if you want, you can write it like this. That's okay. That's fine too. It's perfectly fine. So we have 2. We have this one, and then we have this one. Someone really wants me. I knew I shouldn't have done that. I had to get my car insurance renewed. So I went to one of those websites, you know, where you type in your information and then they give you a price. And I was thinking, they asked for my phone number. I'm like, will I put it in? No, they won't call me. I'll just put it in. I'm like, no, they called me. So don't ever put your number in on a website. I don't know what I was thinking. I was just thinking, they wouldn't go to the trouble of calling me, but yeah. And not only that, they called my wife as well, which is really, really strange because I didn't give them her number. I just gave them my number. So it's kind of like, dudes, how did you get that number? Okay. Right, so we can put these 2 together now. Well, we can combine stuff together. What is the formula for speed? Just back from kind of lesson week 1. Distance over time. So what letter am I using for distance? S. And time? T. But we have a formula, don't we, for S? What's the formula for S? R theta. So we have R theta over T. But what's theta over T? No? This is angular speed, isn't it? So now we have a new formula. The speed is equal to the radius multiply the angular speed. So must be careful because we now have 2 types of speed. This is the speed for the angle, how quickly the angle's changing, okay? So this is like the angle speed. Or angular from proper adjective, but I'll just put angle speed, quotation. But this is the normal speed, the speed we have done in the past, where it's, we call it the linear speed. So what unit do we have for linear speed? Well, that's meters per second, isn't it? And what do you think the unit is for angular speed? Radians per second. So we can easily convert between the two by multiplying by the radius. So now we have three formulas. Okay. I'm going to go down now. Do you have this here? Yep. Okay. So we have three formulas now. S equals r theta. V equals theta over t. Yeah, and then that's omega. Sorry. Omega. And then V equals R omega, yeah. Now, let's go back to my circle. This is moving around in a circle, and it's moving here with speed V, but don't forget that the angle is changing as well here with speed omega. Is this accelerating? Does this have an acceleration? Yes or no?
Yes.
So A, not 0 or A 0? Not 0.
Because it's changing the direction.
Yeah. Did you do this in the SAP?
Yeah.
Yeah. So this does have acceleration because it is changing its velocity. It's changing its direction. So it does have acceleration. So it does have an A. Now, what is the direction of the acceleration? This is actually the direction of the acceleration to the center. Okay. Now, if you think about that, I'll go to the side for the moment. Okay, so he's got his bucket of water and he's swinging it around in a circle. Okay. Now, I'm just talking about horizontally. So, see this rope here? Which way is the force going?
Towards him.
Towards him, isn't it? So if I look from the top, here he is. Here's his bucket. And it's going around in a circle. This is the force here. This way, isn't it? What's Newton's second law? F equals ma. So if the F is this way, then so is the A. So in other words, the acceleration and of course and the force. So let me write that down. Force and acceleration always acts towards the center. And you see this velocity here? It's actually pointing this direction. Velocity is always perpendicular to force or acceleration.
Linear.
Yes, linear velocity, of course.
Does centripetal force have anything to do with it?
Yeah, this force, the force that makes something travel in a circle is called centripetal force. And centripetal is almost like the adjective that means circle. It's not quite like if I said circular force, that's not technically the right word, but centripetal force, circular force, they mean the same thing. It's the force that makes something travel in a circle.
So what's centrifugal?
Centrifuge, okay, it's going to get a bit complicated now. See, centrifuge is the noun for that machine that spins around really fast to separate materials inside a test tube. So I think your one that you're saying is the force that it feels that pushes it out to the edge of the circle.
So like that, okay.
What's that?
Like the bucket.
Like the bucket of water, yeah. But it gets a bit complicated, which I'm going to do in my next example, because sometimes people feel like the force is going out of the circle when you're traveling in a circle, but it's actually still going into the center of the circle. So I'm going to demonstrate that with an example next, okay? Alright, can I scroll down? Do you have those two down? Oh, okay, hurry up. So I want you to think about something. So imagine that you're in a bus or a car. Alright, so we're all in the bus here, and the bus is going down the road and it turns right. Which way do you move in the bus? To the left. So you feel the force pushing you to the left. But which way did I say the force is going? To the right. So what is the reason for the difference?
We feel the
Yeah, it's a type of balance, yeah.
we feel the reaction.
It's the reaction force too, yeah. I'm going to draw it, okay? So can I scroll down now? Oh, I think I need to, sorry.
Can we use like the gravity and the air? Like that?
Yes, that will come into circle, yeah.
Like we don't feel like the air when it's moving because of the gravity.
No, we're getting more complicated now. We'll keep it simple for right now. Okay, so here's our bus, but now it's turning in a circle. Okay. Alright, well actually let me just draw a straight line. Okay, here you are in the bus. So the bus wants to head straight. What does Newton's first law say? Will the bus continue to go straight? Yes, it wants to go straight, unless there's a force. And what about you? Which way do you want to go? Straight also. Now what happens is, when the bus turns, the force is this way and makes the bus go in a circle. But you will continue to go straight. So what's happening is, the bus is moving in, but you're going straight. So then this wall gets pushed against you. So it's actually the other way around. The bus is not pushing you. You are pushing into the bus. Okay? So if you think about it, try to imagine it. I don't really have anything that can like demonstrate it, but here.
The glass of water.
Yeah. I'll just try and make do with this, okay? Person and bus are going straight, but if I just lift it up for a moment, okay, they're both going straight, but as the bus turns, you see, the person still wants to continue going straight. And then they meet the side of the window, and the bus continues to go right, but the person wants to go straight. So it's actually really the person that's more like they're pushing into the bus. They're the problem, not the bus. Yeah?
So the force is a force pushing the bus, but it doesn't push the person inside.
Yeah. There's a force that makes the bus go in a circle. But that's not the force that you feel. What you only feel it really when you get pushed against the window. And then you feel the reaction. Okay? And this can confuse people because they think when something is going in a circle, okay, that the force must be going out. Because they imagine if I'm inside of this, I feel like I'm getting pushed out. But this isn't true. Okay? When it's going in a circle, the force is going in, not out. That's important. Because I've seen that in the exam before. They said, explain circular force, the centripetal force. So the explanation is, or motion in a circle or whatever it was, for something to move in a circle, you need the force to go towards the center of the circle. And you need the velocity to be perpendicular to the force. And then you can have a circular motion. You know? So I'm just trying to get these ideas in your head. Okay, now we'll look at more formulas. So we do have a force, so that means we do have an acceleration. I'll give you the formula. I won't bother to do the proof. I mean, you can read it if you want. But if I go back here, oh, where's it gone? Okay. So what is the formula for acceleration? It is v squared over r. Now, very easy. How can I make this acceleration into an F, a force? Well, what's Newton's second law? F equals ma. So if I multiply this by m, what does it become? F. So I just need to multiply this by m. And here we go. There's our two formulas.
That's all the formulas for the motion in circle, right?
Nearly. I mean, you can just rewrite this last one. Sometimes it's convenient to rewrite this last one here. Remember, what did I say? V equals omega r. So what does v squared equal? Omega squared r squared. You can put that inside here, and instead you get m omega squared r. So you can write it this way as well. Alright, so let's write down all our formulas. What was our first one? S equals r theta. Second one, omega equals theta over t. Thirdly, linear velocity equals omega r. Fourthly, what did I do next? Was it acceleration next? Yeah. Acceleration is v squared over r. Fifth, then force equals mv squared over r, or m omega squared r. So you have 5 formulas for circular motion. Okay. Let's have a look at some examples here. Okay, so please write them down. They're very important. I don't even know if all of these are in the formula book.
I think there are only 2.
Yeah, I don't think all of them are.
Acceleration and angle probably. The main ones, because it's below the...
Yeah, I think you're right, actually. I think the only 2 in the formula book might be the acceleration one and the omega. Yeah, I think so. Yeah. Okay, let's do an example. Can I go down now? Yeah? Yep. Okay. Oh yeah, well, there you go. Yeah, they all are there. Okay. Now, just before I do my example, I just want to clear something up. Well, not clear it up since I've not talked about it yet. Okay. Right. That's a car wheel. Now, what makes this go forward? A force. And where is the force?
Under the center.
Not really, because, I mean, this does not move on ice.
Then on the right edge.
Yeah, so I should put the force here.
Yeah, empty.
Here, like this. Oh yeah, of course there's a down as well. Here's the F. Which way is this wheel turning? Clockwise or anti-clockwise?
Clockwise.
Clockwise. It's going like this, isn't it? So can you just imagine, here's the tire, and it's going to the left, isn't it? So if it's going to the left, which way is the friction going, left or right?
Right.
Right.
So the friction helps.
Much more than that, the friction is the force. So this force that drives it forward, this is actually the friction. That seems a bit strange, doesn't it? But no, it's actually the friction that drives it forward. Now, of course, the wheel needs to turn to make the friction. So, of course, the faster the wheel can turn, maybe it makes more friction. But this is why the car does not move on the ice. Even though the wheel is turning, the wheel turns, the car does not move because there's no friction. Okay? So what's happening is you have the engine, and the engine makes the wheel turn, and the wheel makes the friction. But the friction is what actually is the force. So what's the formula for friction? It's mu r. So I'm teaching you this because sometimes in the question it might ask you, how big is the friction force? And in this case, it's really strange, but in this case the friction force is the driving force. The friction is what allows it to go. Okay, so this is kind of strange, and that's why I'm talking about it. But just so you're clear in your head, in this case the friction is what helps it to drive. So no friction, no drive. Okay, that's just me clearing up some vocabulary. So let's do our example now. Okay, so here's our example. Car is going around in a circle. Okay. And I would like to know, well, let's first write down what information we might know. Okay, so what would we make? Oh yeah, sorry. And to help, I'll draw it twice. So that's from the top, and then this is from the side. So in this picture, which way is the force going? That's side. Side. Sorry. Okay. No, I know my drawing's bad, but it's not that bad, is it? Here's the center, and then here's the center here, like maybe it's a pole.
So what is that?
Okay.
Here, let me help with my phone. So on the top, what you're looking at is the car going around a pole, or a traffic light, or whatever.
Oh.
And then at the bottom, you're looking at it from the side as it goes around. Yeah?
Oh, this is a road.
It's what? This is a road, and this is a pole in the center of the circle.
And those things are doing.
They're wheels. Right?
So this is front view.
Yes. Obviously, that's the front of the car. Yes. Well, actually, I suppose no, it's the back of the car. It's going around up the top. But yes, front view. Okay. So what information might we know? Well, we probably know the mass of the car. So what would we say is the mass of this car? What would we put it as? We'd say 1,000 kilograms, okay? Now, when you picture a car that's going around in a circle, how fast do you think it's going? It's V in meters per second. It depends how big. Maybe 10. And if this is a big roundabout, what will we make the radius?
50 meters.
Let's say 40. There's different sizes here.
You just subtract 10 from all.
What else would I like to know? What else might I know? I think this is enough. Okay, so if you look at my formulas, what could I work out? I've got MVR. What could I work out?
Acceleration.
I could work out the omega, can't I? Or can I?
No.
No, I need some time, don't I?
Acceleration.
I could work out acceleration.
Yes.
Yes.
And
I could work out the force.
Yeah. And from the force you can work out omega.
Could I work out? I could work out omega, couldn't I?
After you work
After you do that, yeah. So just as an exercise to get you started,
What do we need?
I want the missing information. So what am I missing? I'm missing the omega.
Yeah.
Well, I think what did we say was easiest to get first was the A, wasn't it?
Yeah.
The F and then the omega.
Time? Angle? Do we need to find time again?
Yeah, give us time as well. No, just those three first. You know what? There actually is one other thing I do know which we didn't write down. I do know the angle. Wait, listen guys. I do know the angle if I'm talking about one full circle. If it does one loop. Yeah, it's 360 degrees, but then you have to change it into radians. So it'll be, roughly 6.28 radians. You can, yeah. Okay. Do we have the A?
Yeah.
What's the A? 2.5 meters per second squared. So then the force would be 2500 newtons. And then the omega, do we have that yet?
Omega?
No, because you don't know the time. If it was 1 second, yes.
What if you use V equals omega up?
Yes, that would do. V equals omega or. Yeah. V equals omega or. So omega is V over or. 0.25. What's the unit? Radians per second. So it will take how many seconds to do 1 radian? 4 seconds. Alright, now give me the time. I want the time now. Of the full circle, 1 cycle. I want 1 cycle. Have we got that? What formula do you need to use? I think there's only one formula with time in it. Omega equals theta over t.
Yes, it's 8 pi or 25.1.
25.1 seconds. Because you used omega equals theta over t. So t equals theta over omega. Yeah. That is 6.28 over 0.25. Yeah. Okay, I need to scroll down. I'm going to look at this one more. Yes, can I scroll down? So now, let's go back to the side view. It's a car. I should at least put the tires at the edge of the car. Okay. We know how big this force is. What was it? 2,500 newtons. But that's not the only force, of course. There's another force going down, isn't there? How big is that? And let's make G equal to 10, so it's easy.
10 to the power 4.
Yeah. 10,000 newtons. Is that all of my forces? No, what am I missing?
Reaction.
Reaction. Now, is this car flying? No. So the R must equal 10,000. It must equal this. Vertically only. What type of force is this? It's
Driving.
circular force. Makes it travel in a circle. But what type of force is it? It's a friction, isn't it? So this is friction. Now, do you remember what is the formula for friction? Mu R. And the F is 2,500. And the R 10,000.
You're at 25,000.
Sorry, one too many. Okay. So what's the mu here? 0.25. So you could get this in the exam, but they would break it down. You see, in the exam, I'll go back here, don't worry. In the exam, this could be like part 1, this could be part 2, this could be part 3, and then this here, calculating the mu, could be part 4. So maybe it's like 2 marks, 2 marks, 2 marks, 2 marks. So 8 marks. Something like this.
So friction is the turning force.
Yeah, and it's also a turning force as well. Yeah. So maybe part 5 could be what's the turning force. I haven't decided. What letter did I say I'm going to use for turning force? Did I say L?
Yes.
Yeah. Turning force equals, what's the formula for turning force? Force multiplied distance. So here it'd be 2,500 multiply 40. Isn't it 40 meter radius? It is, isn't it?
Yeah, but the why would they?
Oh yeah, but the force is not perpendicular to the distance in this case.
Oh, you're right, actually, it's not. But it's still turning in a circle. Freaky. Uh-oh. That's such a good question. That needs further thinking. This is turning in a circle, but the force is going to the centre of the circle. But it is turning. So that is a turning force. Don't know. No. I've never thought about that before. Force by distance. Oh, wow. Yes, okay. Yeah, sorry. Let's get rid of that. I'm being careless. What's the force here? What's doing the force? Yeah, but what is doing the force? Like, for example, if I open this door,
It's making it moving.
where's the force? My hand, isn't it? Yeah. But this is turning in a circle, so there's a force going towards the center. So I've confused the two in my head. When I turn this here, like this, okay, that's my turning force. But because it's moving in a circle, isn't it? There's also a force this way, and I've confused the two.
So if one went this way, you would say that this is friction.
No. No. This one here would be like the friction. This thing here, that would have something to do with the engines and the wheels. I think it's too complicated to think about. No, I was careless.
turning force?
Could find it, but not by the way I was doing it. Okay. Maybe. We'll see how much we get covered. Yes, sorry. No, not turning force. Okay? It can't be turning force. Thanks, Spanish. It's going towards the center. So that's ridiculous. Okay. Can we get turning force? Let me see, actually.
You can give it closer. Just one way.
Yes. It is not done as an example. Yeah, okay. Right. No turning force. We did not see that. We're continuing on now. Okay, next. I want to do another example with you. And this next example, I've seen it in the exam 2, maybe 3 times. Dan, are you on your phone?
No.
Dictionary?
Yeah.
What word?
I can't.
No, don't be shy.
She doesn't know which word.
You don't know which word you're checking in the dictionary?
So I was looking for turning force, but it's not here.
You don't know turning force?
She knows, but she wants to know how do they call it in Korean.
Ah,
Like in Russian, we have the completely different.
don't worry. Your exam will be in English. So you do not need to know the Korean of turning force. Okay?
Yes.
Great, okay. Now, the next example I'm going to do with you, I've seen this in the exam 2, maybe even 3 times, okay? So here's the example. Well, you know the deal. This is being swung around in a circle like this. I think this is a really good example. It's not done in the book, but I really like this example because it really makes sure you understand circular force, centripetal force. So, can you see what's happening here? It's like I took some rope here and I'm look, I'm turning it this way, okay? I'm not this way, I'm turning it this way, okay? Now, you see the rope has a tension force. Where do you think the tension force is biggest? Top, bottom, left or right? The biggest, or the same even, yeah? You think the same, yeah? Anything else? Bottom? Top? Nobody wants to say left or right.
No.
No. So, we have 3 possibilities. Either the tension force is the same, it's biggest at the top, or it's biggest at the bottom. Okay? Now, to answer this, you just need to picture swinging something. And you know that if you do it slow enough, at the top it could fall down. But you know when it's at the bottom, it always feels really tight. So in fact, at the bottom, this is when the tension is biggest. Okay, so I'm going to write down some first I'm going to draw the forces. Now wait.
So tension at the bottom is the
maximum.
force.
Yeah, now wait, listen. I'm going to draw the forces, but it's important that you know that the forces look different at the top and the bottom. So first I'll do the bottom. What forces are at the bottom? Yeah, there's mg and what else?
Tension.
T. But I'll call it T1 because it's a different tension always, okay? And at the top, what force is there?
Mg.
Mg and
G2.
T2.
It should go.
Huh?
It should go up.
No. It should be like this. Now you see? I can hear your little brains going. That's right. That's right. We're all agreed mg is always down. Yes? But remember I said if you have a rope and I'm pulling something, a rope can't push, it can only pull. So at the top the rope can only pull down, it can't push up. So that's actually right.
So, like, if it wasn't the MG, like, up there, it's going to, like, stay there, not going to move, like, again. Like,
Oh.
No, I'm not so sure. But remember, this is moving in a circle. So which way is the force acting? Towards the center. So at the top, which way is the force going? Towards the center. And at the bottom, which way is it going? Towards the center. So which force is bigger, T1 or mg? T1, because the mg will make it smaller, but it'll still, in total, go towards the center. Now, do you think, next question, the total force, so the total force here, and then the total force here, are they the same or different?
Same.
Well, they're the same, because when it's moving in a circle, it's the same force to the center. Let's look at what we can make. Okay, so we need some information. So let's keep it simple. Let's just say, for simplicity, the mass is 1 kilogram and the radius is 1 meter. And you know what? Let's just make the G 10 as well. Okay. Can I scroll down? I need to scroll down. Yes? Okay. So let's look at the bottom. So how big is this force? mg. So what's that? Come on. How big? What's the number? Guys, come on, wake up. 10. 10.
No, you said. Oh, I know what you said.
10. 10 newtons. And then what's this force called? T1. So I add them together, and what do I get in total? I call it just F. Okay? So I have F equals T1 minus 10. What's wrong? Now, I need to go back and put in some more information. So I'll just put in one more piece of information. We'll say the omega. How fast? Let's just say, we'll say 6.28 radians a second. Yeah. So please add that in. Okay, let's go back. So this formula here for the F, you have two formulas for F, don't you? For circular force. Which one should I use?
M omega squared.
M omega squared.
M omega squared or equals T1 minus 10. What's the M? 1. The or? 1. Omega?
4 pi squared.
Yeah, so 6.28 squared equals T1 minus 10. So T1 equals 6.28 squared plus 10. What's that, please? Is it going to be about 49 or something?
49.5.
Oh yeah. 49.5 newtons. So that's how much tension there is at the bottom. Okay? Now let's look at the top. Can I go down? Yes? Okay, so at the top, what are my forces going down?
G and tension.
Yeah, so that's, how big is the weight? 10. And then this one here, T1. 2. When I add them together, what do I get? F. So I have F equals 10 plus T2. I have M omega squared R, isn't it?
Yeah.
Equals 10 plus T2. So I get 6.28 squared equals 10 plus T2. So this time T2 is 6.28 squared minus 10, which is what that, about 29.5. Yeah, 29.5 newtons.
So it's just 29.4.
Whatever.
Yeah.
Whatevs. 29.5 newtons. I've seen this in the exam in section A and section B. So that's why I say I've seen it at least twice, because I remember seeing it in section A and I remember seeing it in section B. Not the same year, of course. So, yeah, I've seen it twice, at least twice.
Is it possible that in the section B there would be a question which is like the part of the question would be the same as A1 for
No, that should not happen.
like same formula?
No, same formula, but being used in a different way or a different situation, yeah. So, like, for example, section A could have a new equation of motion, and section B could have equation of motion, but two different situations. Yeah. Yes, to where? The last one?
Yeah.
Yeah. Okay. We'll do another example, or maybe not. Hang on, let me think. No, I think I will. I'll do another example. Yes. Okay, and scroll down. Okay, do you have that one too?
Yes.
Yep, okay. It's a plane. And it's going in a circle. But there's a word here in English called banking. So this is when your plane turns at an angle so it can go in a circle. Okay? Right. How many forces here? Well, for sure, mg. Is there a reaction force?
It's fine.
Yeah, we don't call it a reaction force, we call it something else. Yeah, we call it the lift force. It's the force from the wings. So when the plane is going straight, Joshua, put your arm down, you're too relaxed, turn around, there we go, that's better. When the plane is going straight, we have this situation, mg and L. Okay? But when the plane turns, we have this situation. Okay. Now, let me just call this here L. So this is just L. Right. I'm going to resolve these two forces here. So that way and that way. And let me call this one here theta. So how big is this force? L cos theta and L sine theta. Okay. What can I say about L sine theta? Must equal mg. Right?
What is the question?
Um,
What are we going to do?
I would like to find theta. I think I'll try and do this. Yeah. I'm looking for theta. And I'll tell you what else you know. The other information you know. The information you know I put in red, okay? So we know the mg, and we have L here, and it's going in a circle, okay? So we can know the radius and we will know the V.
Radius, V, and M.
Yeah, so I'll write it down here, yeah. We know the M, the V, and the R. And I want the theta. Okay. So I have L sine theta equals mg. Joshua, why is that? You told me it. Didn't you say it? Well, why does L sine theta equal mg? Why? Come on, give me a full sentence.
The rate's equal to the.
Yeah, well, yeah, go ahead.
If it was like different, maybe again it's competition, it's like it's direction.
Yeah, almost. If they were different, if the L sine theta was bigger than the mg, what would happen? The plane goes up, and if it was less, it would go down, but it's staying here in a circle, so the L sine theta equals the mg. Okay? Now, what do I know about L cos theta? Well, not turning force, yeah, we don't want to make that mistake again.
There's the force.
It's the force that's making it go in a circle, isn't it?
Yes.
The force that makes it go in a circle. We have two formulas for that.
MV squared
Which one should we use?
MV squared over R.
We should use mv squared over r. Okay. So I need to put these together to get theta. So I have L sine theta equals mg, and L cos theta equals mv squared. Is it over r? Yeah, it is over r, yeah.
So we can
So
find L and
we could find L. I mean, this looks a lot like when we were doing our ladders against the wall and all these types of problems. So here I should find L. What does L equal?
mg over sin theta.
Mg over sine theta. And here,
MV squared over.
yeah, mv squared over r cos theta. So I put them together and I get mg over sine theta equals mv squared over r cos theta. Okay, so what cancels here? M's. Anything else? No. So what I'll do is I'll bring the sine up to the right and I'll bring the r cos up to the left. No. Sorry, let me think about that. I'll bring the sine up. Yeah, I'll bring the r up and then I'll bring the v down. So I'll end up with sine theta over cos theta equals g r over v squared. Who remembers what sine over cos is? Tan. So you end up with this. Tan theta equals g r over v squared. I've seen this in section A. So the section A question would say something like, here is a plane with velocity v, mass m, traveling in a circle with radius r, and then they give you the picture as well, the diagram. And then they would ask, show that tan theta equals this.
Oh.
So I've seen that in section A once, maybe twice.
Can they just ask to find the theta?
Oh yeah, they could have given you numbers and asked for the theta. So because they gave it twice, I don't think they would ask it again. They might. But they could ask something similar. Like for example, I'm picturing this situation, okay? Can you listen? Exam advice time. So they won't ask this again, I don't think. But they could ask something really, really similar. Like for example, they might say, you know when you have those racing tracks, the cars go really, really fast, and the road actually is not flat. The road is an angle, so the car can go around really fast. Or, you remember when at the Olympics, when they're cycling indoors, and they have the little track and they go around and around and around, it's an angle. Okay. In fact, it's the same formula. That the angle depends on how big the circle is and how fast they're going. You get the same formula. The only difference is instead of lift, you don't have lift. What's the name of the force? Reaction. But when you look at my proof, everything's the same, isn't it? There's no difference. So, yes, you could get this again, but they won't do it with a plane, an aeroplane. They might do it with like a bicycle on a track or a car on a road.
As long as it's in an angle.
As long as the surface is at an angle. So this is what I mean about physics. You don't get the same problem in the exam, but you get something that if you read it and picture it, you can say, that's like the plane example Stephen did. Yes? Okay, you might not think the exact words like that. Okay? So that's an important example. And this is the thing. Those two examples I did with the bucket and with the plane, they're not in the notes, okay? Because the reason I did those examples is because I saw them in past exams. Okay? So books are good, online videos are good, but it's the notes, well, I wasn't going to say Stephen is the best, but the notes in class are best for you. Okay? Right, did you write that one down? It's important. Okay. So actually, when I'm looking at the questions here on page 69, I can already see one question that's like that. Look at 69.
6.
Yeah, number 6 is a car, and the angle is 20 degrees. And then number 5, I did something like number 5, the car going around. Okay. Number 1, what do you know? You know the radius. What else do you know? You know or, you know V, and I want the average velocity from A to B, is it? Number 1 is stupid, don't do 1.
Which was the
Yeah, let me see. Stupid. Right. Okay, just a quick check here. Wait. If something is turning 5 times per second, how long does it take to turn once?
0.05.
0.2. Yes? So the t is 0.2, and what's the angle? 2 pi. 6.28 radians, 360. Okay. What word do we use that means to turn in a circle? It begins with an or.
Radian.
Yeah, revolve, revolution. Yeah. Did you do a lesson with Stephen on that word, revolution and revolve? No, that's what you'll do this Friday. Okay, you'll do on Friday's ESAP lesson, you'll do vocabulary to do with circular motion. Okay, so anyways, revolution or revolve. Okay, I would like you to do, and you can start them now. 2 to 6. 2 to 6. Yes, actually. Yeah, sorry. Let me look at from 2 to 6. Not
including 6.
including 2, including 6, including between 2 and 6. Okay. 2, 3, 4, 5, and 6. Okay. You can start them now. I want you working on these for a few minutes, okay?